Hi everyone, I'm Jack, and today I'll be presenting PEak, which is a single source of truth for hardware design and verification. And this work is being presented on behalf of Caleb, who was not able to make it, and was done as a part of the Agile Center at Stanford. So the motivation for this project was pretty well introduced during the beginning of PLARCH in the morning. Essentially, during the creation of a hardware design, you typically have an ISA specification. It can be written in a text document or a PDF that looks something like what I've shown on the left. From that ISA specification, you need to generate a couple of different things. Typically, you have a functional model, maybe in a high-level language like Python. You need to generate your RTL design. And if you want to do any type of formal verification, you need a formal model as well. It's really important that these three representations of your ISA are equivalent. And in our group, we address this by adding this sentence to our website. Just please make sure that your spec matches your design. Obviously, this is not a great solution to this problem. So we had to test these different representations against each other, right? So to test the functional model versus the RTL, we used unit testing. So we did different configurations of our design, send in random values, and made sure that they were equivalent. To test the formal model, we used formal tools that would either test various assertions or equivalence between the RTL and the formal model. And so in this project, we were trying to kind of rethink this whole process. Specifically, we were trying to answer the question, what does the ideal specification look like? We came up with 4 different features. First, it should be easy to read and write. That's pretty obvious why it's important. Second, it should be a functional model. Third, it should generate RTL. And fourth, it should be a formal model, right? If you have your specification generating these 3 different representations, that would just be a better way of doing it. And there's been a whole bunch of work in this area. And I've listed a whole bunch of different projects in this slide that are organized into 2 categories. The first at the top is more hardware HDLs, right? And at the bottom are more ISA specification languages. So the ISA specification languages like ILA, SAIL, and ISA formal typically have formal representations, but don't generate RTL. And then most of the HDLs will generate hardware, but might not have a formal model or be directly executable. Right? So PEak is most similar to Lava in that it has 3 different representations. It's directly executable, it has a formal model, and it generates RTL. However, they're different in the fact that PEak is written in Python instead of Haskell, and uses algebraic data types, which I'll get into a little bit later in the talk. So I talked about what the ideal specification language looked like. What if this was the specification? Here I'm showing some PEak code on the left. It looks like just regular Python, right? There's a class at the top that defines an opcode. That's an enum type. It has 3 different potential values, add, sub, or negate. And below that, there's an ALU class. This inherits from PEak and has a call method. This call method defines the inputs and the outputs of this ALU. So we have an opcode of the type defined above, and 2 inputs, I0 and I1, which are of type BB16. We also define that it has 1 output. In the body of this call method, we have some if statements that kind of decode what operation we're trying to do and then return the appropriate operation. Right, so this is pretty easy to see that this is easy to read and write, which is basically just Python code. And assuming we have definitions for like enum, PEak, and BV, it's relatively easy to see that this would be executable. It's a little bit less easy to see how this would generate RTL or how it would be a formal model. To introduce how PEak does this, I will talk about hardware types. So hardware types is a formally defined type system that we've created for PEak, and it includes abstract interfaces and type constructors for a number of different types and kinds that are particularly useful for hardware design. In particular, we have bit vectors and algebraic data types, like sums and products. The semantics for hardware types are derived from SMTlib, and they have 3 different concrete implementations for every operation on a hardware type. First, it's executable in Python. Second, there's a formal model in SMT. And third, we can generate RTL from those operations through a hardware description language called Melchert, which can be compiled to Verilog. So if this is some PEak code, and this represents your ISA specification, we can now, through the power of hardware types, generate 3 different representations or 3 different interpretations of this ISA specification. The first, through Python, is a functional model. This is useful when writing your hardware design and you want to obviously test the functionality. Second, through Magma, is you can generate RTL. And the third, through SMT, is a formal model. So now you only have one ISA specification and you get all 3 of these things automatically generated. So in the next couple of slides, I'll go through what it looks like to generate a little bit more of a complicated ISA specification and how you would do functional verification and formal verification of that specification. So here I'm showing on the top left a little bit more complicated of a processor instruction. It uses algebraic data types, specifically enum and product types. So you have opcode, which is the same as before. It has add, sub, negate. And now we've added a new enum type called reg control, which has 2 potential values, accumulate and input. And then below that we have this instruction product type that combines the 2. So here we have op, which is of type opcode, and control, which is of type reg control. From this really simple example, you might be able to see how this is quite a useful way of describing processor instructions. Below this, we have the same definition of ALU. And to the right, we have a little bit more complicated description of a reg ALU. Here in this class, we have now 2 methods. First is init. Within init, we instantiate both an ALU, which is defined in the lower left, as well as 2 registers, reg0 and reg1. Then within the call function, we have 3 inputs, the instruction that we defined in the top left, as well as 2 bit vectors, n0 and n1. Then within the body of this call method, we create a new variable called out. We set it equal to the output of ALU, which we configure with instruction.op, so the opcode part, as well as the output of reg0 and reg1. So we're reading from these registers. Then we have an if statement. We check to see what value reg control has. If it's accumulating, we set the input of reg0, the output of the ALU. Otherwise, we set it to the n0 variable. Finally, we set the input of reg1 equal to n1. So if we wrote this specification and we wanted to test some property about it, how do we do that in PEak? So say, for example, we wanted to make sure that the value in register 1 is always equal to n1. To do functional verification, we do that really easily in PEak. Since this is just a Python class, we can instantiate it like normal Python. And we can loop through all the different values for our instruction. So we can go through the add, sub, and negate, as well as the different values for reg control. Instantiate the instruction, which is a combination of ALU op and reg mode, and set some initial state within our processor. So we create random bit vectors for ALU.reg0, so the value of reg0 and reg1. We then create random input variables, I0 and I1, and simulate the ALU, so we can just call it like a normal Python function. Then we assert this post condition that says ALU.reg1, so the value in reg1 is equivalent to I1. We run this for all different possible instructions and a whole bunch of different random state and input variables. We can have a reasonable guarantee that this is always true. But you might want a formal proof. So we also include a formal model in PEak. In order to do some formal verification, instead of doing random bit vectors, we create SMT bit vector variables, so symbolic variables for the initial state from reg0 and reg1, as well as some symbolic bit vectors for I0 and I1. We use a helper function to convert the instruction into a SMT representation of the instruction. Then again, we set the initial state to be these symbolic variables, and we can symbolically execute the circuit. Again, checking the same condition that the value in reg1 is equivalent to I1. The query, the SMT query that we actually send to a solver is on the right. We say that, does there exist some instruction and some initial state and some inputs into this PE, or this processor, such that the post condition is false? If this does exist, then we know that there's a bug. Otherwise, we have verified that this property is true. So we've been developing PEak over the past couple of years, and within the Agile Hardware Center at Stanford, we have used it to generate a couple of different chips. Here, Amber and Onyx were fabricated, and they worked. So PEak is capable of producing high-performance hard work. Additionally, the unique features of PEak have enabled some really interesting projects. The first of which is a compiler synthesis project that leveraged PEak's formal interpretation. So within this compiler synthesis project, essentially what we're doing is synthesizing a set of rewrite rules for a specific processor, and combining that with an instruction selection algorithm to adopt kind of any to a compiler to any sort of PEak processor. Here, a rewrite rule is essentially describing how you perform a operation, so in this case, subtract, on a PEak processor. Both of these are formally specified, and a rewrite rule just says what is the configuration of this PE such that it implements the subtract. We can create an SMT query that says there exists some instruction such that for all inputs, the output of subtract and the output of the PE are equivalent. If we do this for every single IR that we care about, or IR node that we care about, we then can combine that with instruction selection algorithm in order to create or synthesize this compiler for whatever architecture we want. Additionally, we also use PEak's metaprogramming ability, since it's just Python, to do this design space exploration project that I presented earlier this year at ASCOS. In this design space exploration project, we created an automated flow that took an application data flow graph, did some application analysis, created this kind of abstract representation of a processing element that is intended to accelerate this application, and then ran that through a PEak specification generator. This translation process from the abstract PE graph into PEak was really straightforward because PEak has good metaprogramming ability. We then leveraged the PEak compiler as, in addition to the project that I described on the earlier slide, in order to do application evaluation for every PE that we were generating in this design space exploration project. So yeah, in summary, PEak aims to be the ideal specification. It's easy to read and write, and it has 3 different interpretations. It provides a functional model, this is just executable Python, it generates RTL, and it is a formal model. PEak has been used in the creation of several chips, some of which have been fabricated, and it has enabled several different interesting projects. So thank you.